Okay, I will introduce myself. My name is Miguel, and I'm HPC architect at Lenovo. Some of you already know me from many years, so I am the guy that already 5 years in a row I'm here presenting some view of what Lenovo sees in the technology landscape, and that's what I want to share with you, some little view that I want to put in contrast with your thoughts and of course share what our worries may be regarding our data center infrastructure. So today I want to share the next minutes with you telling about what we see in the technology landscape regarding the advent of the exascale era and how our clusters are getting denser and denser and how we can keep up with this evolution while not spending too much money in power and also not putting our data center on fire. Well, I think I will use a manual control. It's better. Okay, so maybe you have already heard these days the announcements of the European Union. Some of you already for sure have heard about that. The announcement of the European Union to fund 3 different hosting facilities for pre-exascale systems that will be located in Finland, in Italy, and one of them very near here in Barcelona Supercomputing Center, which we'll be visiting tomorrow morning, I believe, according to the agenda. Okay, that means that those centers will multiply by 20 or by 30 their computing capacities that they now have. That means starting from 200 petaflops of computing capacity, which is a huge amount. And in our view, the energy efficiency is going to be key in the design of such systems if we don't want to get on fire, as I said. So this is the innovation we want to work on, and we see the water cooling systems a key player in the development of these systems. So to have a rough idea of what we're talking about with the traditional air-cooled systems, we can provide more or less 5 teraflops per node as a mean, but now with the advent of accelerators and also not only GPUs but also FPGAs and other kind of accelerators, we're going to be able to provide a sustained performance over 50 teraflops per rack unit, which is a lot. Meaning that maybe for every rack we can start drawing power over 80 kilowatts. 80 kilowatts per rack is a lot, and maybe this does not affect only to pre-exascale systems, but also to smaller systems. As we know, we are as HPC users, we are used to adopt the trending technology, the latest technology, but maybe at a smaller scale. So that's why we also have to take into account the power consumption and the energy efficiency. Also, if we have just one rack. Well, you know, this is the landscape of what the processors and coprocessors and accelerators is showing. Currently, the top beam processors are drawing a power of around 150, 180 watts, even 200 watts. And we are seeing an increase to keep up with the Moore's law. We are seeing an increase of the power consumption if we want to keep up with this evolution. For instance, the recently launched product by Intel, the Cascade Lake AP processors are drawing in the top bin SKU around 400 watts per CPU, and it's a general purpose CPU, very powerful, but general purpose. If we talk about accelerators, then we're starting seeing power draws of 300 watts and beyond. Not only about processors and accelerators, but also persistent data, memory DIMMs of persistent data, as recently launched also by Intel. The generalization of use of NVMEs inside our machines one single NVMe drive is not very power consuming, just 20, 24 watts. But we are able, with so many PCI lanes in our system, and also the advent of PCI 4, is going to provide a lot of bandwidth. So we are going to be able to populate lots of NVMe drives, in maybe 24, maybe 32 drives inside a single system, which is also very power hungry. And if we want to cool those systems with traditional air cooling, with traditional fans, that's also a cause of us spending a lot of money in electricity. Okay, so we have higher power processors. We have to take into account our data center limitations. We have to contract the power source, and also we have to pay the electricity every month or every year, and this is going to be a pain. And not only those costs in terms of financial, so to say, but also in environment penalties, I would say. That could end up by us capping the performance of our own systems, because we cannot run them at full speed because we don't have enough power to feed them. And there is another variable that we want to add, and we want to see as an opportunity to be more efficient in terms of energy, is the waste heat we use, the heat we dissipate from our machines that does not get lost in the air as we used to do currently. So regarding power efficiency, we are used to deal with this number, which is the power usage effectiveness, the PUE, traditional, we know what it is the relation between what we spend in power according to the real power we can use for our IT equipment, including the cooling infrastructure. I mean, all the chillers and all the CRAS that we want to use for our data center. So there could be a more another number that can reflect also the difference between or the relation between what we spend in our IT equipment, including the built-in cooling and power and cooling components, which are maybe the power supplies, the fans, and the voltage regulators, and the power we use for real compute in our processors, memory DIMMs, hard drives, etc. That's something also to take into account. So at the end, what we want to know is, what we want to optimize is the relation between the energy we pay for and the energy we use for compute. And that's all about energy efficiency. And there is another number that we want to take into account, that is the energy reuse effectiveness. That means is the PUE, but discounting, subtracting the energy we can reuse for other purposes. We can talk about this in the next minute. Cooling technologies. Well, this is the traditional approach to cool our data center in a hot aisle and cold aisle layout as traditionally, and not very efficient by itself. Always we have to help with some kind of contention, air contention, something like that. We have to help those systems to get cooled in an efficient manner, and in that case, is not very efficient. Next step to traditional air-cooled systems is to provide rear door heat exchangers. That means installing in every rack in the rear door a water loop, a water coil that cools the hot air that is coming out of the machines, and so that the air that goes to the hot aisle is already cold. That's this is the approach that, for instance, Barcelona Supercomputing Center is following traditionally, and well, and it's the same approach as the air cooled, but much more efficient. But now we have said that next generation processors and coprocessor is going to draw a lot of power, and if we want to go dense, very, very dense, and it's going to be a must, that is going to be very, very difficult to cool by traditional methods with air. So that's why we are approaching this issue with direct water cooling. That means that we are going to make water circulate in a water loop inside the compute node, cooling all the relevant components such as the processor, memory DIMMs, network cards, or hard drives. That's very efficient, and we can describe a little bit in the next minute. So what this consists of, and see how why this is much more efficient, getting some PUEs much lower than the ones we were getting with traditional air cooling. And as I said, also we want to approach this this way of cooling things, also reusing the heat dissipated with the water loop, reuse it for other purposes, and we can see also a little bit how it works. Okay, Neptune is the I would say that the project, the Lenovo project, to address all those energy efficiency challenges that we have with our dense state-of-the-art dense systems, and that's something that we have put in production in several places. See here, as I recently mentioned, BSC is using rear door heat exchangers. LRC in Munich is using direct water cooling, and also this approach of energy reuse. And in many other places in the world, we have already these systems with different approaches. So basically, what we are doing with Neptune is use liquid to do things, to cool things, and with different approaches. Already mentioned the rear door heat exchanger. That's a concept that we already know. We have the direct water cooling, the direct to node, we call it, because we cool directly the relevant components of the node. What we call the thermal transfer module, that it's a heat sink with liquid in the inside that transports the heat from the very place of the CPU to the rear side of the node, helping the air removal, the hot air removal. That's something that it's kind of a hybrid cooling, and also we are providing some smart control software in order to change the governance of the CPU frequency at runtime by means of analyzing the behavior of the applications themselves. That's a software called Energy Aware Runtime, developed in collaboration with the Barcelona Supercomputing Center as well. Well, I will focus then on the direct water cooling approach. Well, as the paradigmatic example of energy efficiency in a supercomputer, we showed the Leibniz Rechenzentrum in Munich, the so-called LRC for the French. It's the number 8 supercomputer in the top 500 list. Remarkably, it's the number 1 supercomputer in the world that is not using accelerators, no GPU, no accelerators of other kind. And they are using processors that are drawing around 240 watts, which makes necessary to cool directly with water. Having said this, well, it's a very powerful system, around almost 20 petaflops of Limpac performance. And we have calculated the energy reduction compared to a similar air-cooled system in 45 energy reduction. And doing some math, it's estimated to provide energy, or to save energy that could provide energy for 5,000 homes every year. So it's a system, to have an idea, is about twice the Barcelona, the Mare Nostrum 4 and in BSC. and well, this is kind of paradigmatic. I will show why. Well, this is the layout, the description of a compute tray in the LRC installation. So it's a tray that has 2 compute nodes, and the only components they share no components except the water loop and the power supplies, and that's it. So we let the water circulate on the 2 nodes, on all the relevant components of the 2 nodes, with warm water, and this is the key thing, that we are able to cool. I mean, to maintain, to keep I will say a good operating temperature of all components by putting in water at 50 degrees Celsius. And then we circulate the water over the components and let the hotter water go out to the outlet, and that's the way we can keep our system properly cooled. Even we are able to. Sorry, I'm a little bit cold. I have a cold. So that's why we can be efficient at cooling it, and even kind of overclock the capabilities of a compute node. As an example, Intel designed specifically the SKU that they are using for this specific system. Well, it's a little bit of the description of how it works. So we put conductive plates under the hard drives on the CPU themselves instead of the traditional heat sinks, and some pads that remove also the heat from the memory DIMMs. This is a view of a chassis of 6 compute trays. That means 12 compute nodes that have the inlet water circuit and the outlet water circuit. As for the rest of components, it's a regular node. It's a dual processor node with 12 up to 12 memory DIMMs and all the capabilities that a regular compute node may have, except that it may host higher thermal components because of this direct water cooling characteristics. So why water? Why water and regular water? Okay, first of all, it's in terms of financials, it's cheap. Maybe in terms of environment, it's not that cheap, but it's kind of cheap, and we can make it recirculate as many times as we want. And also compared to air, it can absorb, it can store 4 times the energy that air can host as well. So that's why this is more efficient than air. And also, by the use of a water loop, we can drive the water in a more efficient way than air with regular fan assembles. And this inner copper water loop, why is it made of copper? Because it's a very efficient material at conducting, and also in terms of efficient in terms of financials. Very efficient at transferring the heat very rapidly, and that's key. That's the key thing why we can use hot water up to 50 degrees to remove the heat from the components of our compute node. That's why we have chosen the copper. You can see some other cooling technology vendors that are doing things that more reusable. I mean, more universal, so to say. That that can use some kind of other materials, but maybe they are not so efficient. That's the trade-off. This must be customized for this specific system. If we talk about copper. So at the end, we get hotter water. I mean, when I say warm water, I mean hot water that can be used to cool things, and hot water is the really hot water that goes out of a circuit. So, what we can do with this hot water that comes out of the compute cluster, that we can simply chill the water and let the heat escape to the universe. That's really energy waste, or we can reuse this hot water, for instance, to feed heating systems in our greenhouses or small offices or any other use we can give it, or even to get warmer in a swimming pool, in an inner swimming pool. This would be their direct reuse. And there is an indirect reuse that consists of using the energy of the hot water with the heat dissipated in order to produce, again, cold water, chilled water, and be used to cool some other things. I will try to explain a little bit how this works, although I'm, of course, no expert in thermodynamics. Maybe here in the room are people that can explain it much better than I. But what I have understood, I will try to explain with my own words. So in LRC, they are using absorption chillers, which is, the absorption is a process that uses a certain material that is kind of heat hungry, that can absorb particles that can attract particles that are really hot, and transfer the heat of those particles of those water particles in this case to transfer the heat to itself. Then condensing again the water particles already cooled, already chilled, and put it in the circuit again. So that's why partially we get some chilled water that will go to some other places that need chilled water. For instance, maybe not all the installation is using direct water cooling nodes. For instance, our storage system or something like that must be cooled with air or rear heat exchangers or something like that. And we can use this chilled water for that. And as this is not 100% efficient, that would be the perfect machine, then we get warm water, but not as warm, not as hot as it came out of a compute. And then we can reuse this warm water to cool again our compute cluster. This is more or less how I understand it works. I mean, and it works. But of course, for physics or thermodynamics, please ask someone else. Sorry. Well, this is another description. 10 minutes left. Okay. Yes, more than enough. I'm almost done. No, but maybe we can use the rest of the time to discuss a little bit. So, well, this is more or less how it looks like, an absorption chiller, and well, it has two modules, and in each one where they produce chilled water to feed some other cooling systems, and on the other hand, we get warm water to keep cooling with warm water our compute cluster. This is more or less the approach. So on one hand, we have the direct water cooling, which is very efficient at cooling the compute nodes themselves, and on the other hand, we can reuse the energy, the very same energy. We can waste energy, so to say. We can reuse it for other purposes. That's the good thing of it, and this is how in LRC is working, and it's kind of producing very good results. They are also using this energy-aware runtime software that is also saving a lot of power in the usual production. Maybe I believe that they are already in production, but if not, well, they have the system up and running so far. And last but not least, there is another approach. This is not used in LRC, but this is another approach for the next generation ultra dense compute cluster. So this is immersion cooling. Our friends of Submer will tell us about this invention, a very interesting invention. Later on, and you can see one of these immersion tanks outside at the entrance of this building, and for sure our friends of Submer will be happy to show you how it works, and it consists of dielectric liquid cooling almost any kind of hardware, as long as it doesn't have any moving parts in it. That's it. I mean, no spinning drives and no fans. Of course, no fans. We don't need any fans because this is already cooled. And we are already using SSD drives as a standard. So it's not a big deal. And also with I believe that with spinning drives with certain conditions, they can also cool that stuff. Of course, they are the ones that know about this. The good thing I see is that almost every hardware, you don't have to design this for a specific piece of hardware, not with a tailored water loops that need to cool every component in the node. So you don't have to care about that. You just put your server or your switch inside this tank, and then you start doing things with it. Advantage is that it can cool, if I'm not wrong, maybe these guys can correct me, but I think they can cool in a 42U form factor. It can cool up to 100 kilowatt or so. Is that okay? Okay. Okay, and it's getting better over time, I believe. And in fact, Lenovo and Submer are already collaborating in some proof of concepts that are running somewhere, and of course that's another approach that in certain environments may make sense, and we certainly see this as a promising approach, complementary to direct water cooling or any other kind of approaches we are working. So this is what I wanted to share with you today, and as Jordi said, I agree to him that this is a knowledge sharing meeting. So I would like you to share with me if at some point in time you think that this thinking of energy efficiency may affect you at some point in time. I mean, maybe your systems are not as big as those very big supercomputing centers, but maybe you kind of see that in the next future you're going to need some of these approaches. Just feel free to ask.
I'm interested in knowing how these water inlets and outlets from the system and to the system affect in the difficulties of cabling and putting the systems in place. What do you think about that?
Yes, it could affect. I mean, the serviceability, yes, of the system might be affected. In fact, because it's something that you have to take care of. Regarding cabling, in this particular system, this is a next scale design, the old design, I mean the traditional design by Lenovo with front cabling. So in terms of data cabling, this is done on the front, so it does not affect at all. So yes, just the power supplies are connected on the back side, but that's something that does not interfere with the service. We can see the picture here. Yes, you can see the picture here. Now here are the power supplies, and these are the water outlet and the inlet. So it's not affected. Of course, if you have to service a node to change a memory DIMM or a processor or something inside, of course you will have to close the particular water loop in the corresponding tray, and then you will take out the tray and do whatever you want. And you have to do it for two nodes. Even the failing node is just one. It's a trade-off.
More questions? I guess that a lot of people would love to have a spa next to a data center, right? Just to reduce the heat, I guess.
Sorry. Yes, it's standard water with certain conditions of quality of water, but regular one. I mean, nothing very special, no special liquid It's no special liquid, no special dissolution, nothing. It's regular water with certain conditions of pH and that stuff. But yes, it's regular water.
Any more questions?
What are the tolerances for the input? What are the tolerances for the input temperatures? Say if you've got a really cold water supply.
Sorry, I don't hear you properly.
No. What if you've got really cold input temperatures? Is it variable for the system to work out?
Well, I believe there is a minimum temperature. I mean, this direct water cooling works with up to 50 Celsius, and the minimum temperature, there is a minimum, I can't remember, but it's, I can give you the data later on, but I believe it's around 10 degrees or something like that, which is cold enough. Obviously, if you are in the somewhere in the Nordics and you're getting the regular, and as it is regular water, you can take it from everywhere. And maybe the water can be at a lower temperature, then you would have to manage it to recirculate it somewhere else and get it a little bit warmer. But I don't have the exact minimum temperature.
Any more questions? So, well, Miguel, thank you so much.
Thank you.